All right, so the next module we're covering is on exponential functions. And I wanted to start off with a quick review of exponents. Of course, we all learned exponents as repeated multiplication. So something like 4 raised to the third power means 4 times 4 times 4, which is 64. But what about exponents that when we work with exponents that are not positive integers, natural numbers, we have to use basically the way this works to develop our other exponents. Of course, it makes sense that if you have the same base raised to two different powers, that you add the powers, because of course if you had like 2 cubed times 2 to the fourth, you'd be multiplying 7 2's altogether. Also, if we divide, we subtract our exponents, and that's because if you had something like 2 to the, we'll do the, in fact, the exact opposite of the one we did above. If you had 2 to the 7th over 2 cubed, if we have 7 2's multiplied together on top and 3 multiplied together on the bottom, 3 of the 3 on the bottom would cancel, and that would leave 4 2's multiplied together. So we subtract the exponents there. The multiplication rule is similar. If we have a power raised to a power, we multiply those, because if we had, say, 2 cubed squared, we'd be multiplying 2 cubed times 2 cubed, and that would be 6 2's multiplied all together. All right, so those are our exponent rules, and we can use those then to derive what other powers are. Like, it makes sense that anything to the first power is just that number. I don't think we'll go there, but the reason why some people get confused with the x to the 0, anything to the 0 power is 1, because if you think about like 2 cubed over 2 cubed, we know that's 1, but by the subtraction rule for exponents, that would be 2 to the 3 minus 3, which is 0. And obviously anything divided by itself is 1. All right, negative exponents also can be derived by the power rule. So if we say x to the negative a, that's the reciprocal. There's two ways to derive that. One is if we did, say, 2 cubed times 2 to the negative third, then we'd add those powers together, but that's 3 and negative 3 is 0. So that's 1. So 2 to the negative third is the reciprocal of 2 cubed. But the other way to look at it is that if you had the subtraction rule and you had 2 cubed over 2 to the 7th, the subtraction rule says that's 2 to the 3 minus 7, or 2 to the negative 4. But if we actually canceled that out, we'd see that there would be 4 2's left on the bottom. So there's two different ways to see the negative exponent. Okay. Another one is if you have a fraction, we'll do 1 over n, where n is an integer, positive integer. That means the nth root. Okay. So why does that work? Let's say we had 2 to the 1/3. Okay. And let's say we cube that. So then if we cube 2 to the 1/3, that would be 2 to the 1/3 times 3, which is 2 to the first, which is 2. Well, if I have a number and I cube it and the answer is 2, then that number is the cube root of 2, by the definition of what the cube root means. So when we have a fraction like that, 1 over n, that means the nth root. And then, so then if we have m over n, we can write that one of two ways. It's the nth root of x to the m by multiplication, or the nth root of x. Do the root first and then the power. It doesn't matter which order we do that in. The hardest ones to understand are the irrationals. If you had something like x raised to an infinite decimal, basically you have to do that by what it's close to. And that's a little bit beyond the scope of our course. But the understanding the exponents is important because now we're getting into exponential functions. If we, for a moment, go back to linear functions, remember y equals mx plus b. We know if you start off, we know if we do an xy table for this, in fact, let's even do a number, y equals, let's just say 2x minus 3. We start when x is 0, we start with the y-intercept of -3. And then each time we add 1 to x, we add 2 to y, so because of the slope. So the slope is the number we add each time. So we add, so when it goes from 0, -3 to 1, -1 to 2, 1 to 3, 3 to 4, 5, and so on. Each time we add 2 for the y. All right, so in a linear function is repeated addition. Well, now we're going to talk about an exponential function. So an exponential function is one where the variable is an exponent. So it looks like this: f of x equals b times a to the x. All right. So your variable is your exponent. You got a multiplication, a number multiplied by a base to the exponent. So let's give a pretty simple one. Let's do f of x, and we're going to do a table of values for it. Let's do 3 times 2 to the power x. All right, so let's do an xy table for this. All right, so if we plug in 0, 2 to the 0 is 1, so f of 0 would be 3 times 2 to the 0, which is 3 times 1, which is 3. So the number in front is the y-intercept, just like the b is the y-intercept in a linear function, the b is the y-intercept, tells us the y-intercept in an exponential function. Well, so now as each time we add 1 to x, though, what happens is I'm going to multiply by another 2. So now I have, when I do f of 1, I have 3 times 2 to the power 1, which is 3 times 2, which is 6. All right, when I do f of 2, that's 3 times 2 squared, which is 3 times 4, which is 12. So I got 2, 12. And then the next one will be 3, I'll double it again, 24. 4, double it again, 48, and so on. All right, what if I went negative? What if I went the other way? -1. All right, what would happen in that case is, if you think going to the left, each is just like in the linear function, if I want to go left, I would subtract 2 instead of add 2. In this case, if I want to go left, I would divide by 2 instead of multiplying by 2. 48 divided by 2 is 24. 24 divided by 2 is 12. 12 divided by 2 is 6, and so on. So now if I have 3 and I want to go left 1, it's going to be 3 divided by 2, which would be 3 halves, or 1.5. And then at -2, I divide that by 2, which would be 3/4, and so on. All right, and as I keep dividing by 2, it'll get smaller and smaller. All right, if we take a quick look here at what this graph looks like in Desmos. In fact, I'll do both of them. I'll do y equals 2x, 2x minus 3. That was y equals 2x minus 3. And then we're going to do y equals 3 times 2 to the x. That's what 3 times 2 to the x looks like. In fact, maybe I'll do the first one as 2x plus 3, so they have the same y-intercept. All right, so let's see here. Let me put that, throw that in the notes real quick. All right, so the red one is y equals 2x plus 3. And the blue one is y equals 3 times 2 to the x. So we see the exponential function on the left. If you keep dividing by 2, you'll get closer and closer to 0. But dividing by 2 would never make it negative, so it has a horizontal asymptote on the x-axis. So for f of x equals 3 times 2 to the x, we can see the domain. You can use any number as an exponent, so the domain is all real numbers, negative infinity to infinity. But the range, this function will only spit out positive numbers, so that's 0 to infinity. With no parentheses. We have a horizontal asymptote. Remember, horizontal lines have the form y equals. So the horizontal asymptote is y equals 0. One other thing to note is 0 to a negative is undefined, 0 to 0 is undefined. And negative powers get really complicated as well. So for this, I forgot to write at the top, a is positive. B is not 0. If it was 0, the answer would always be 0. And a is any positive number except 1, because 1 to any power would just be 1. So that would just be a horizontal line. So we have positive numbers there. All right, so that's what 3 to the 2x would be. What if we had a fraction as our exponent? So we're going to look at a graph like y equals, let's do the same thing for the a, but do 1/2 to the x. Well, there's two ways to do this. One is to just go back and try our table of values. Only this time I'm going to go from start in the negatives, -3, -2, -1, 0, 1, 2, 3. All right. And 0 is the easiest because anything to the 0 is 1. So that would be times 3. So actually, let's call this g of x instead of y. So g of 0 is 3 times 1/2 to 0, which is 3. 3 times 1. G of 1 would be 3 times 1/2 to the first, which is 3 times 1/2, which is 3/2. So this actually is exactly the opposite of the one above. Since multiplying by 1/2 is the same thing as dividing by 2, as I go to the right, I'm dividing by 2, and as I go to the left, I'm multiplying by 2. So like g of -1 would be 3 times 1/2 to the -1, but that -1 exponent means take the reciprocal, so it'd be 3 times 2, which is 6. So going left, this time I'm multiplying going left and dividing going right. That's just like a negative slope is the reverse of a positive slope. All right, so 12, 24 going right, and then going left, and then 2 would be 3/4, and 3 would be 3/8. So if I draw the graph of this, it's literally going to reverse the direction. So if I do 3, y equals 3 times 1/2 to the x. So now the green graph is that graph. All right, let's see here. Let's grab this one. All right, so the blue again is still y equals 3 times 2 to the x. The green, though, is y equals 3 times 1/2 to the x. But remember, 1/2 to the x would be 2 to the -x. So that's why this is just a reflection across the y-axis. 3, let's write that over here. 3 times 1/2 to the x is the same thing as 3 times 2 to the -x, because it's the reciprocal. So, y equals 3 times 1/2 to the x has the graph of 3 times 2 to the x reflected across the y-axis because we negated the x. I'm not going to go through it here, but all the rest of the transformations are the same. If I added or subtracted a number to x, that would shift it left or right. If I added or subtracted a number after the 2 to the x, that would be up or down shift, etc. So those shifts all still hold. Okay. So the biggest thing, though, that one of the biggest things we use exponential functions for is growth by percentages. So if we have something that grows by a certain percentage every time period, like a good example is if you invest money, you hope that it grows by a certain percentage a year. So we're going to do an example with that. That's, to me, is the best thing about exponential functions, is it helps you in terms of think of how you would invest money. Suppose, let's pick just an easy number to work with. $1,000 is invested. Is invested at, or let's say in an account that has an average return of 5% per year. How much will the account be worth in 20 years? All right, now the way usually people learn to do this, and like when you do percents in middle school, is you do $1,000, you multiply that times 0.05 for 5%. That's the decimal version of 5%. Percent means out of 100, so 5 over 100, which would be 0.05. That would be $50 would be the interest in 1 year, and then you would do 1,000 plus that 50, so we'd have $50 after 1 year. All right. So then, but let's write that a slightly different way. Let's do the next year. So that'd be 1,050 times the 0.05 again. But I'm going to say plus the 1050. So do it all in one step. Let's see here. Let me get my calculator out to do it. So we get the answer. But then we need a shortcut because I don't want to do this 20 times. But let's see here. 1,050 times 0.05 plus 1,050. All right, so it's $1,102.50. All right, so that's after 2 years. So we made $100 after 2 years, or $102.50. That's not bad. All right, so there's an actual shortcut. If I factor out 1,050 here, I end up with 0.05 plus 1. Well, that's obviously 1.05. So that 1.05, that's 100% plus 5%, or 105%. So if you increase something by 5%, you add 5% to your original 100%. So you can just, in one step, multiply by 1.05. Well, in 20 years, I would take my $1,000 I started with and multiply it by 1.05 20 times. So I would do $1,000 times 1.05 raised to the 20th power. That would be the shortcut way to raising my money, or sorry, to earning 5% for 20 consecutive years. So if I did that, 1,000 times 1.05 raised to the 20th power, and I would end up with 2,653 rounded to 30 cents to 26.5330. All right, so that's the shortcut way, is to add your percentage to 100 if you're increasing, or you could subtract it from 100 if you're decreasing. So the function, the amount of you'd have after any number of years t would be 1,000, the amount you started with, times 1.05 raised to the power t. So the just like in the a times b to the or b times a to the x, the 1,000 is our starting amount, and then the 1.05 is how much I multiply by every time period, every year. Okay, so let's do a reverse one where we decrease by a certain percentage. So let's say a car depreciates, which means loses value, by let's say 12% per year. If the purchase price is $30,000, what is the car worth after 10 years? Okay, depreciating is you lose value when you buy a new car. It loses value over time. All right, so let's see here. In this case, our A of what I need to do is I need to do 100% minus the 12% depreciation, and that's 88%. So that means 88% is the remaining value at the end of each year. So 88% of the previous year's value. After each year. Okay. So then my multiplier is 0.88. I convert that to a decimal. So the amount, the value of the car, I'll say V for value after t years, is given by the initial value, 30,000, times that 0.88 raised to the t. And our question is the value after 10 years. So the value after 10 years, V of 10, is 30,000 times 0.88 to the 10th power. So let's type that in the calculator, 30,000 times 0.88 raised to the power 10. So, it just did 30, I missed the times. That would be helpful, 30,000. Not minus, times, there we go, 0.88 raised to the power 10. That should give me a better answer. There we go. $8,355.03 if we want to be extra accurate. 8355.03. All right, so the value of the car, if it depreciates at 12% per year, after 10 years will be $8,355.03. Okay. All right, I just want to add one more thing, and I think that'll be enough for today, which is in interest, sometimes we, instead of compounding it every year, we still give the annual interest rate, but we compound it every half a year or every 3 months, every quarter, or every month. We call that periodic compound interest. Suppose we're going to go back to that first thing. The $1,000 is invested we're going to change the interest rate just to make the division easier. 6% interest, or let's say I'm going to say annual interest, but it's annual interest, but it's compounded. I'm going to say monthly. All right, what that means is we're going to pay 1/12 of the 6% every month. So 6% divided by 12 would mean we get 0.5%, 0.5% each month. All right, so that means our total we get is our 100% plus our 0.5% is 100.5%. And so our multiple would be 1.005. Oh, let's say, how much is the account worth? Sorry, I didn't add that. After 20 years. All right, but I have to be careful since I'm paying the interest every month. I have to take that 20 years times 12 months per year. That would be 240 months because I'm going to pay the interest 200 every month. So now the way I calculate it would be 1,000, my initial value. My multiplier is 1.005 for 0.5% every month, raised to the 240th for 240 months. So let's type that in, 1,000 times 1.005 raised to the 240th power. And I get 3,310.20, 3310.20. $3,310.20. Let's look at it if it had just been every year. That would be 1,000 times 1.06 raised to the 20th because it's 6% each year. And the answer is I'd have over $100 less. So compounding every month made me get more interest because what was happening was I was getting interest on the interest I had already made.
Wait, I'm sorry. Where did you get the 0.06?
Oh, because of the 6%.
Oh, okay.
Yeah, I'm seeing what if I had just paid 6% at the end of each year instead of dividing the 6% into 12 months and paying 0.5% every month. So it's just
Okay.
a comparison.
Perfect.
Yep. All right. So there's actually a formula for this. So the formula. All right. Formula for compound interest. All right. And so we're going to say P is the principal or initial amount. We're going to define some variables or constants. Is the principal, which is also is another name for our starting amount. Principal. Sometimes I put that as A0 because we do A subscript 0 because we do A of T. R is the interest rate as a decimal. That's important. So we've always been using it. So like 6% is 0.06 interest rate as a decimal. Oops. All right, that's R. And then we have N is our number of compounding periods per year. I think that's everything I need to define. All right, so in this case, that was 12 because I had 12 months per year. All right, and so here's what it is. So it's A of T, the amount after T years would be your principal. And then what I did was I took 1, but this time instead of adding the R to it, I divided the R by the number of compounding period. I divided the R by 12, and then I added it to 1. So up here, that was where I did the 6% divided by 12, changed it to a decimal, which was 0.005, and added it to 1 for 100%. And then that's raised to the power N times T. That's where I multiplied 12 months per year times the 20 years to get 240. All right, so if you use that formula, you can calculate interest compounded over any frequency. The most common ones are monthly or daily. So daily, obviously, the N would be 365. In banking, I think they actually use 360 because they just basically call it 30 per month for ease of calculation. But I'm not going to get into that kind of complication. You can just use, if it says daily, you can just use N equals 365.
And that formula can only be used in the last one we just did?
Well, in theory, you could use it on any of the other ones. It's just that N would be 1. So like if you're compounding the interest once per year, the N is 1. So if the interest is, so if the, let's say if the percent is only added or subtracted once per year, or I mean, T could be something other than a year, but that's the most common one. Once per year, the formula is A of T equals P times 1 plus R to the T, because the N would be 1 in that case. So R over 1 would be R, 1 times T would be T. And the R is negative if it's a percentage decrease. So that's why I did like 100 when I had the car depreciation problem. The R was negative 12%. So I did negative 0.12, 1 minus 0.12. But when it's interest, when you're gaining money, when you have something that's increasing in value, you add that percent to the 1. All right, so yes, so
Okay.
the first formula I will give you on the test. You do not have to memorize the first formula. The second formula is pretty straightforward, and it's a special case of that first formula, so I'm not going to give you the second formula as a separate formula.
Okay.
All right, so there's only one other formula in this, and I'll give you the formula, but I'm not going to go into its derivation right now. Just so this will allow you to do all of the homework in module 10. And this is the formula is if you keep making the compounding period shorter and shorter, eventually it converts to something called continuous compound interest. And what that formula becomes, and a lot of people have seen this before, P times a number called E raised to the R times T. And E is just a special number. It's approximately 2.71828 and so on. But that's on the calculator. If you just want the number itself, you can hit second and the divided by key. That's E. And if you want to raise it to the power without using the exponent button, you can hit second and the LN button on the left, and it gives you the E with it ready to do an exponent. But you can just do the 1 by the divided by key and do the caret to get the exponent. So in this case, if I redid the previous one where I did 6%, if I had the very end here too, of course. All right, so in the last example, the P was 1,000 and the R was 0.06 and the T was 20. So I would just do 1,000 times E raised to the, and then that was, the R was 0.06 times 20. So 33, 20, 11, so even a little bit more still. But this is the most you could ever get by compounding. So this is called continuous compounding. All right, Bianca, thanks for coming so that I wasn't just talking to myself.
No, it's totally okay. Thank you so much.
And now you don't have to watch the video.
Yeah.
All right, so this is all the stuff you'll need for the homework for module 10. So, but that won't be due till next week. All
Okay,
right.
perfect.
All right.
Thank you
Have
so
a
much.
great day.
You too.